All right. So let me check the time is good or not.
The time is 1 o'clock. So just 1 minute. Okay, it's just a time.
Yeah.
So maybe you also still wait for about 5 minutes, or we just no?
I think we can start, and I will make the recording. And once you start, yeah.
Okay, just recording is right. It's in the process. So okay. Just share this. Okay, that's full screen mode. I just set it full screen mode. Get started. Okay. Okay. Hello, everyone. I'm Jun Chi from the from Fudan University. Previously, I got my PhD from Georgia Tech. Today, Hawk and I will talk about this one important and very interesting topic about quantum machine learning. And we'll talk about the theoretical foundations and also we just introduce some applications on these two devices. So let's get started. In my part, there are about 4 parts. Firstly, I'll show you some background about what is the quantum machine learning, why should I engage in such a topic. Then I'll show you some the 2 important paradigms about quantum machine learning. One is based on variational quantum circuits, and another one is about the quantum kernel learning. In the third part, I will show some applications for speech recognition based on the quantum computing. Maybe Hawk as a part will show some details about automatic speech recognition based on quantum kernel learning. But in this part, I will show some basic ideas, basic applications about based on variational quantum circuits. In the fourth part, then we will maybe it's going deeper. We'll talk about this theoretical foundations of quantum neural network to show our latest work about this variational quantum circuit based quantum neural network. Okay, let's get started. This is just outline for today's tutorial. This tutorial will last 2 hours. In the first 45 minutes, I will show my part is the solid foundation for about this quantum computing and quantum computing for machine learning. So let's get started. Okay, everyone is very familiar with deep neural network. Deep learning has achieved astonishing improvement.
Is the video still running? Can you hear from Jun?
No, I cannot hear.
Okay, let me check with him. All right, so since Jun is disconnected. Yeah, Jun, you are mute and disconnected. So would you like to share your screen again?
I think there's a pause.
Yes, you are mute and disconnected. Yeah, now it's good.
Okay. Just disconnected. I thought just it's okay now. Okay.
Yes. Yeah, please share your screen and keep going. Yeah. Yeah, you should. Are you mute yourself? Yeah. And M2, can you add me as a host? Thanks.
Okay, just say
you can keep going.
Okay, no problem. I want to start about this introduction about the problem of my Wi-Fi. So this is because of the 2 important factors about hardware and it's about the training data. Because we don't care about too much about this theory behind the deep learning. So many people describe deep learning as alchemy. So maybe it's the engineers from Google, Amazon, and other big companies that is focus on engineering tricks. For example, how to set up this model architecture, how to use optimization algorithms, how to do the regularization to improve the generalization of deep learning for different kinds of machine learning tasks. But our work is a little bit different, and we want to find out is the mystery behind deep learning. So in my thesis student, my PhD study at Georgia Tech, with maybe a focus about is why deep learning can work so well in practice. So our finding, our discovery side, if we can set as the deep learning as an over-parameterized neural network, maybe the test loss can go down exponentially. This is very different from the classical machine learning. For classical machine learning, if the model parameters get larger, maybe it's even count. So the classical machine learning, it's difficult for them to get out of this overfitting domain. But for the deep neural network, maybe it's, if you can set it as over parameterized setting, maybe it's very, maybe it's at some threshold. If it goes go beyond the threshold, maybe this test loss can exponential going down. There's a mystery why this deep learning can work so well in practice. But the problem is that you want to consuming the over parameterized deep neural network. It means that we need to not size model parameters. Okay, so this obstacle exists here. So one important obstacle is that the development of this hardware cannot catch up with the development of the demanding for over parameterized neural network. About each 18 months, maybe the number of the model parameters can increase by more than 35 times. But the Moore's law means that for each 18 months, maybe the computational power can be doubled. So there is a big gap between this the over parameterized deep neural network and there is the Moore's law for development of GPU and CPU. So this is why we are engaging these quantum computing. We will want to make use of quantum power to accelerate this classical AI architecture. Because for current this Moore's law, maybe it's cannot to increase the computational power to support the development of artificial intelligence based on this over parameterized deep neural network. Okay, this is our basic idea about how to do this work. For classical deep neural network, maybe there's a big gap between theoretical study and empirical study, as I mentioned. Maybe it's some people working in large big companies, working in large tech minds, they don't care about the improvement of theoretical study on deep neural network because maybe they by somehow to fine-tune the model parameters. Maybe they can achieve very good performance in practice. But the improvement of maybe some new discovery about the theoretical study of deep neural network have to develop the quantum machine learning. Because currently the quantum machine learning is still in early stage. Early stage means that we only have a few hundreds qubits. So maybe it's currently the theoretical study, the empirical study, and in the same place in the domain of quantum machine learning. So maybe some theory from classical deep learning is very useful for such development of the quantum machine learning. Okay, this is the motivation by engaging in this quantum computing for classical artificial intelligence. And that's just briefly introduce the quantum computer. We just use a very brief sentences to describe the quantum mechanics. Okay, these are currently some big companies such as IBM, MQ, and Google. Maybe they set up their own computers. For example, Google, IBM just set up the quantum computers based on the superconducting qubits. And IBM just released its roadmap for the future development. Maybe this year, they just released the quantum computer that's based on these it's an ego machine, maybe they call it ego machine. It carried have us about more than 400 qubits. Last year, it's only about 127 qubits. And maybe they will announce the quantum advantage in 2019. And at that time, there's only about 27 qubits. But next year, maybe it's, if everything goes well, maybe the IBM will release a more advanced quantum computer with more than 1,000 qubits. And in 2025, maybe the qubits number maybe reach about 1 million. At that time, it means that we have a much better quantum computer to support many machine learning and finance, and maybe other materials science work. Okay, this is some application plan. Maybe it's your label for machine learning next year. This year is 2022. Maybe next year, vast majority of the machine learning work can be supported by quantum computer, because the requirements for the machine learning, the qubits number is about 40. Or the only needs a physical qubits, about 40 physical qubits to support vast majority quantum computing, quantum machine learning work based on quantum computing. But for more complicated tasks, such as finance and machine vision sort of conversion, and maybe it's a drug discovery based on AI technology. Maybe it's need more algorithmic qubits. And for example, for the finance, we need about more than 250 algorithmic qubits. So maybe the neighbor year maybe is much longer than this machine learning applications. Maybe it's 2026. But for our topic about the quantum machine learning, maybe next year we'll see exponential growth in such a domain. This is why we just want to introduce, maybe it's just give us a tell today, because that's a time we engage in this body, in this field. Okay, just what's the difference between this classical computing and quantum computing? I just want to use a picture to describe the difference between the two computing paradigms. For the classical computing, at one time, maybe the computer just want to represent one point in a sphere. But for the quantum computing, maybe we just make use of the superposition and entanglement characteristics. The superposition means that at one time, not only we just represent only one point, instead we can consider all the linear combinations, all possible points at one time. So if we run or simulate one experiment, we will consider 2 to the n possible possibilities, 2 to the n possible results, compared with only one result conducted by the classical computing. So this is one difference. It doesn't utilize a super parallel computing capability. And entanglement means that it's only 2 qubits, no matter how far the 2 qubits is. But if there is get entangled, the one state of the qubit can directly affect another qubit, no matter how far the distance of the 2 qubits. Okay, this is the superposition property and the entanglement characteristic involved in quantum computing. We want to use such as characteristic to set up machine learning models. Okay, this is the explanation about this quantum computing. Currently, we're just in the area about knowledge intermediate, also this type of knowledge intermediate scale quantum devices. This we call it the NISQ devices. What's the NISQ device? It means that we don't have so many quantum with a quantum base. Instead, so we do have to spare so many quantum base for the error correction. So we have to consider if we do have very noisy qubits, what kind of application we can do now. So this in the future, we expand fault tolerant quantum computing, but now we only have as the NISQ device. So maybe, but unfortunately for quantum computing, for the machine learning application, this NISQ device can support vast majority machine learning applications. Okay, from last year, we just introduced our work in so many conference venues. For example, last year, we just want to show our first discovery of our application of how this quantum computing for machine learning in EJK. And last year, we have Hug and I as a co-host who invite so many experts in such domain to introduce this in this field. Maybe this year also we have I'll have to set up some special session in ICASP. Next year we have a new one. So we invite some experts and researchers in different research institutes and the university to participating in our special sessions. Okay. Well, just want a brief introduction to the backgrounds about why should we engage in the quantum computing for machine learning, and what's the quantum mechanics, what's the difference between the classical computing and the quantum computing. And next, I would like to show you two important quantum machine learning algorithms exist nowadays. Maybe you can, these two algorithms are too popular. And I'm going to give a brief introduction about two algorithms. And then the third part, I will show this application for speech recognition based on the variational quantum circuits. Maybe it's a hug, maybe give you some more examples about this, how to use a quantum kernel learning for speech and NLP applications in the second part. And another part I will show is our latest very fancy work about this end-to-end quantum learning. Okay, so this just a pipeline about the variational quantum circuits based on quantum neural network. So this first, in such architecture, we can see that there are three parts for variational quantum circuit to compose a quantum neural network. The first part we call is tensor product encoding. And what's the tensor product encoding? The function of this tensor product encoding is to convert the classical data y. Y is a non-vector in the classical space. They want to use the tensor product encoding to convert the classical vector into the quantum state. And here, just the quantum state, we consider the superposition, and we consider the entanglement. So maybe here, we just do the data conversion from the classical data into the quantum states. Then we have a parametric quantum circuit. Parametric quantum circuit is very similar to this classical parametric model in machine learning. There is some fine-tuning and adjustable parameters. By fine-tuning these model parameters, we can fit output and input data. So maybe it is a data-driven model. Then finally, there is a measurement operation because of the uncertainty about quantum computing. Each output of this parametric quantum circuit is uncertain. Maybe with some probability to output by doing the measurement with some probability to maybe output at zero. Maybe some probability to output as a minus K1. So the output, we will take the expectation values. If there's we do measurement many times, maybe the expectation value maybe becomes a stable value. So we just finally we just connect the classical expectation values as output for post-processing. And post-processing maybe is for the classification task, maybe for the regression task. So this is a basic idea, a basic components to compose the variation quantum circuit. So the first part is tensor product encoding, and the second part is a parametric model that we call it a quantum parametric model because the parameters is made of the qubits. Finally, it's a measurement and down to convert back the quantum states to the classical expectation values. Here it is, we run this experiment many times, maybe it's more over 1,000 times to get expected values. Okay, this is the basic framework about the variational quantum circuit for the composition of this quantum neural network. Here is how to train such as a variational quantum circuit based on quantum neural network. It means we just make use of this classical machine learning optimization algorithm. For example, some IDM, SGD, various algorithms. This is the CPU-GPU interaction in this training process. CPU will be responsible for what kind of algorithm we choose and how to control this learning rate. And the GPU just stores such a variational quantum circuits. and maybe the also outputs the measurement classical values to give feedback to the GPU to the CPU. Okay, that's a very easy implementation of this variation quantum circuit for this new quantum neural network. In 2020, we have a very interesting paper about this part. We suggest the implementation of variation quantum circuit-based quantum neural network for implementation of the reinforcement learning. That's a paper and gets the first reward in Shannon quantum machine learning competition. This paper has been cited more than 120 times nowadays. So maybe from that time, that's where we start to take more focus and take more time in doing the quantum machine learning. Okay, in this work, we just it's the first time to use a variation quantum circuit to implement this the reinforcement learning. For classical deep Q learning, maybe that deep Q learning just replace the lookup table to just build up the input and output relationship between the states and this Q value action. But in our quantum reinforcement learning, we want to replace that deep Q learning neural network with the architecture shown here. We just use the Vigorcy to replace such as deep Q learning neural network. And then we want to use the other classical machine learning optimization algorithms just to fine-tune the Vigorcy model parameters. And the experiment that shows that after several hundred episodes, finally we can get better results in a very simple frozen lake simulation environment. It is for such a simple lake environment, we can also use our dynamic programming to easily find a solution. But here we don't want to use reinforcement learning or maybe the quantum reinforcement learning to find out whether we can use such a quantum computing to find the best solution. And the answer is yes. Even we use only 4 qubits or maybe 5 qubits, if we consider the output, maybe use a 5 qubits because really to run some experiment on a real quantum computer. It's our work in 2019. Okay, this is the basic idea about this variation quantum circuit and this introduction about the application about based on quantum reinforcement learning, we can implement the reinforcement learning. That's just an introduction to quantum kernel learning. Quantum kernel learning is just basically called it the very similar to the name, to the title, the kernel learning. So, yes, sir. We want to just follow the classical kernel learning paradigm. Only one difference that we don't use the classical kernel. Instead, we want to use a quantum circuits to help us to compute this kernel function. So instead of just find a mapping from the data space to the feature space, you want to find this quantum circuit and to set up the quantum circuit to find a map to form this input space into the quantum hyperbolic space. So this one, without the quantum circuit like this, maybe there's a UI and the UIs and the quantum circuits. Maybe use such even the randomized quantum circuits to speed up the computation speed of the quantum computing. So the output is this quantum kernel value, the quantum kernel values. Images if we run such as experiment many times, they'll take the average. And then the final results very close to the theoretical kernel values. So even if you use the quantum computer, maybe to execute the computation or the kernel learning, maybe the computational complexity can be reduced from n squared to log n. So I think this is exponential speed up if we use a quantum computer to calculate the kernel functions, the kernel values. That is a big advantage if you want to use it. Another, if we get these quantum kernel values, we can just use SVM or other kernel methods to find for this classification and regression task. So maybe this is a much more efficient algorithm. And there is one important thing that if we use the kernel method, maybe so we just use a quantum kernel space, it have a better representation powers than classical feature space. Why is it like that? Because for the quantum circuits, it has a larger representation capability. We just want to mention that in our last part of my tutorial. So we mentioned the quantum circuits have a larger representation powers than these than the classical circuits in the feature space. Okay, after the calculation of this quantum kernel, you can just use this perceptron classifier to find out this classification task, to find out do the classification task or do the regression work. Maybe this algorithm, quantum kernel learning is very efficient algorithm nowadays. Maybe they can achieve the state-of-the-art results by using such as a quantum kernel learning paradigm. Okay, this is a basic introduction about these two important quantum machine learning algorithms. One is based on variational quantum circuits, and another one is quantum kernel learning. In this part, I just give you some basic idea about this. And then in the second part, give you more examples about the real applications in the computer vision, NLP, and this speech recognition, about how to use such algorithms to set up the real systems. But in my part, in the third part, I'll give you some our brief introduction about these simple applications. How to make more details about it. Okay, the first application is a Haswalk in 2020. At that time, we just want to use a random it's a quantum convolutional neural network to feature extraction, about speech feature extraction. Maybe instead of using the time series speech go through the end-to-end occlusive modeling, instead we want to that these speech features go through the quantum convolutional layer. And the quantum convolution layer maybe can be randomized initialized. We don't want to fine-tune such a layer, but we want to use a randomized layer, quantum layer, to feature extraction. So here, as I mentioned in our previous chapter, we see that the quantum circuits has a larger representation power than classical neural network. So when I compare these, we can see that maybe if we use a quantum convolutional neural network, we have as a this cumulative capability based on the quantum convolutional encoded features is much better than the classical neural convolutional encoded features. Here, the feature A is just input mirror spectrogram. It does that the input mirror spectrogram, mirror spectrogram, maybe goes through separately goes through this the first convolutional neural network. The second is a quantum convolutional neural network. We see that maybe the outputs of quantum convolutional neural network features is more discriminative. Okay, so this our paper results, our results maybe can also corroborate our observations. So we just use more full qubits, and the results based on the convolutional encoding, the quantum convolutional encoded features. The best results compare with we use a classical mirror spectrogram features for this baseline architecture. Or maybe it's also better than we use the convolutional encoding features. So in this experiment, we want to highlight the most important thing that if you use a quantum convolutional neural network and encoded features, we can have a better represented speech features. Why is that? What's the mystery behind this? And the mystery is that the quantum the quantum models have a larger representation power than classical machine learning deep learning models. That, for example, we use the quantum convolutional neural network. It has a better representation power than the classical convolutional neural network. So this work, we just want to empirically prove that. Okay, this is one example about is the application of the quantum machine learning for speech recognition. At that time, only have about 10 qubits. So we don't use this qubits and quantum model to set up the cursor model. And we want to use the representation power capability to set up to extract features because it has better better representation power than classical computing capability. So okay, this is one example about this the quantum machine learning quantum neural network based on variation quantum circuits for ASR. Another one is our last year work. Because at that time we only have about 20 qubits, and in the first application we have about 10 qubits, and the second application we have about 20 qubits. So we can make use of the qubits and the quantum model to partially replace the classical Bayesian architecture. So in this work, we consider if we use a quantum neural network to partially replace a deep neural network, and we can follow the pipeline to see architecture in our hybrid quantum classical neural network, what's the performance look like. So in just such architecture, we have used a CN model as a pre-trained model, and the QN model just combined with the pre-trained model for our new hybrid model. So in the target task, we just fine-tune the model parameters about quantum neural network, and when we followed this convolution neural network. So this here just the architecture about this CN framework. Here we first use to train is the based on this CN plus the DN. A second architecture we just replace the DN with the quantum neural network, and here we just follow this convolution neural network and only consider the fine-tuning model parameters of the quantum neural network. So last year we have some experiments. If that baseline just a scene past the DN for classification, a scene for the feature representation, feature extraction, and then we want to replace this DN with a quantum neural network, and then also use the pre-trained CN. And our result that use such architecture, we have even better result compared with the baseline. This the simulation on this GPU CPU environment. It means that we don't consider quantum noise. But if you want to place such a model on a real quantum computer, what's the performance like? Okay, have some comments. Those parameters mentioned here, they are CTC based on our result. Okay, thank you for the recommendation. Okay, so if we want to place the model on a real quantum computer, the performance can be degraded to some extent, but also maybe catch up with the baseline result. Okay, this is our new hybrid quantum classical neural network for speech recognition, which has published this work last year. Okay, maybe it's a hack, maybe have more applications about this, how to use this hybrid quantum classical neural network for natural language processing, maybe for the computer vision. But here, just give you one example about how to use it to set up a hybrid model for speech recognition. Here, it's just not speech recognition. That's speech command recognition. Maybe it's a little bit different between speech recognition and speech command recognition. Okay. Okay, we just give two examples of the use of this variational quantum circuit for in practical speech processing applications. But there's some problems existed for this variational quantum circuit based on models. One obstacle is that limited representation capability if the target function is non-smooth, is non-convex, because the unitary the variational quantum circuits just correspond to the unitary transformation. Unitary is a unitary transformation, just a linear transformation. So this if the target function is non-smooth, then it may come non-convex function. Maybe it's how to boost the representation power of such as a variational quantum circuit is one obstacle. It's one our concern. The second one is that the Barron-Plateau optimization problem. Barron-Plateau means that ideally, even if one want to optimize the VQC-based quantum neural network, there indeed there is one path from the bottom of a mountain to the top of a mountain. We want to find such a path to optimize the graduation quantum circuit. But in practice, we can't find such a path. Instead, always stay on the horizontal line. It means that also we do so many fine-tuning process, but the Tesla laws cannot degrade it. Cannot be lowered to a small scale. Also, but we also maintain to a very large Tesla laws. So it's a stay on the horizontal line. There's a problem we call it the Barron-Plateau. So how to overcome such a Barron-Plateau problem? In our latest MPJ paper is a Nature paper. So how can I just release this Nature paper to just introduce some new algorithms, new methodology to overcome the Barron-Plateau problem and how to boost the representation power in practice. Okay, just the last part, I'll just introduce our Nature paper. In this work, we also focus two important improvements compared with the obstacles. Focus obstacles of the previous VQC-based quantum neural network. One is how to introduce nonlinearity to this the VQC, because the VQC is as a unitary linear transformation from the input quantum states to the output quantum states. So how to introduce the nonlinearity? The second important issue is how to overcome the optimization problem we call it Barron-Plateau. So that's why we just introduced such a model. We call it a TTN VQC model. The TTN is a tensor model. The tensor model is commonly used in machine learning. There's originally from the mechanical, it's a classical mechanics in physical domain. Now, in the recent work, there are so many the use of tensor train network for the feature dimensionality reduction. Maybe it's just use a tensor train for classification task. Here, we just not only simply to introduce a tensor train network, we want to try to introduce tensor train network, only one layer tensor train network, only one layer tensor train layer to impose the nonlinearity to this VQC model. And this, just as I mentioned, there are three parts of VQC model. The tensor product encoding for feature, quantum feature extraction, and then it's a parametric circuit for just with adjustable qubits. And finally, this measurement to output the castle expectation values. Okay, then we want to focus. That's the first important thing that we need to introduce such architecture. We just introduce how to use the tensor train network to impose nonlinearity to boost the representation power of the VQC model. And the second thing that was kind of set up to overcome the Barron obstacle optimization problem. And then we want to focus the Tesla laws. Tesla laws is coming up bounded by the sum of three components. One is the adder of representation power as a representation loss. The second one is estimation loss. And the third one is optimization loss. So we separately to see each loss, what's the factor determine this each loss, and how to further upper bound each loss. Okay, first important thing that we want to introduce one layer and the train layer. It's maybe tensor training the classical machine learning and classical deep learning. You can reshape the fully connected layer into the tensor train format. And if you do that, and maybe we can use a much smaller model parameters to maintain the baseline performance. I will have several interesting papers for speech classification, for the speech recognition, for speech enhancement based on tensor train neural network. And more importantly, the tensor train layer can physically find equivalent quantum circuit to send it to place on is a real quantum computer. It means that for classical neural network, it's incredible to find the quantum circuits to represent it. But if the fully connected layer of the classical neural network can be converted into the tensor train network, we can find equivalent quantum circuits to represent the tensor train layer. So in such an architecture, in practice, we can find out is an untrained quantum architecture. So there's no classical neural network getting involved in such architecture. Instead, we only use all the quantum circuits to represent to realize, such as quantum circuits. Okay, this give you one example. For example, if we want to consider this tensor train layer, we can use equivalent quantum circuits to represent this classical tensor train layer. I use such as this equivalent quantum circuits to compose this the one layer of tensor train layer. So this variational quantum circuit is the tensor layers. You can compose of tensor layers, and such as it also can be composed of quantum circuits. So from the beginning of input to the final output is end-to-end quantum, and totally is quantum model. There's no classical model involved. So that's consider that classically for the classification task, we use the hybrid model. Hybrid model, some model from classical neural network, and the final classification is based on the quantum neural network. And in this work, from the very beginning to the end, we just the whole pipeline is based on the quantum models. We don't use the classical model at all. So this is a very interesting thing. That's why we just want to introduce this the tensor train layer for the feature to add some nonlinearity in the feature here for the feature space, and also we got to use it for the quantum implementation. Okay, so the end-to-end quantum neural network. Okay, just give you some theoretical understanding about this our TTM accuracy. TTM means that it's just a tensor train layer for the feature dimensionality reduction and the feature and introduce some nonlinearity to the feature in the feature space. The accuracy is just the classical accuracy model. And then firstly, we consider the representation power. And then our finding is that it's just the upper bound is very inversely proportional to the number of qubits. And it also is very related, inversely related to the constant measurement. It means that you will have more qubits. Maybe it's currently we use 20 qubits, you have more than 100 qubits. The representation error can be further reduced to a small scale. And if you want to do more measurement, it means I will have a more stable expectation output for the post processing. Maybe representation power for the TTM accuracy model can be further improved. Okay, this is the simulation based on the different qubits. Where we use the simple 8 qubits and the 12 qubits. We just compare that if we use the 12 qubits, the MAE loss for regression work can be even further reduced. Okay, another thing more important is about generalization power. Generalization power maybe is more related to the training data. The training data is the target training quantum data, and also maybe is related to the quantum waves. Ideally, we just want to set up is over parameter setting, but in practice, it's incredible to do that. So maybe instead, we just consider if we can set up this model as to satisfy the PL condition, we can better overcome the obstacle of a Baron-Pareto obstacle problem in the process optimization. So here that we do have the PL condition set up. Maybe when we found this Baron-Pareto problem because the test laws just stay in the same horizontal line. It means that we just fine-tune the model parameters many times, but test laws is still at a very high level. But if we want to really satisfy this PL condition, maybe this test laws can be go down to a small scale. So the problem here is that how to set up PL condition. In this work, we think our model satisfy the PR condition. Because if we want to set up as an over-parameter setting, we can easily just find the setup for the PR condition. But in many applications, how to set up this is one important concern. And our finding is that you can make use the pre-trained model. If you use, for example, that's our previous work, we use the SIN as a pre-trained model as the initialization for the hybrid model. If you use, make think about how you use the pre-trained model at the startup, maybe we can easily find the set of PR condition for better overcome the Baron Prado problem. It's our new finding. I also do some theoretical work, but one empirical studies to support this work is for our application for speech recognition. We just find maybe it's a pre-trained SIN model. I use a free SIN model for feature representation. Maybe if we only consider fine-tuning this the quantum neural network, maybe we achieve even better result. So this is a very interesting thing. So in our work, we may consider to pre-train this tensor train layer instead at the very beginning. So here we just is end-to-end training. It's a very from scratch. We just to train this tensor train layer and the variation point circuit. Maybe if we can retrain this tensor train network, we can better to satisfy. It's easier for us to satisfy the PR condition, so we can better overcome a better Pareto problem in the training process. Okay, this is our finding and some brief introduction of new theories in our Nature paper. Okay, maybe it's this end of my part. And how can we give more examples based on quantum kernel learning for speech recognition and for natural language processing and for computer vision? Okay, this ends my part. Thank you so much. Thank you for your attention. Thank you so much. Okay.
All right. So thank you, Jun, for this theoretical foundation. And are there any questions? Yeah.
Hansen has some question.
Yeah, no, actually, sorry, not a question. I actually just want to make a comment because I attended Jun's last seminar, and I asked a question about the kernel, quantum kernel, why it assumes the particular form that it does. Your slides, yeah, that one, the question 2. So basically, if you don't have the norm squared, it's still the kernel. So the inner product would be a kernel. So actually, I did some research. So basically, the norm squared can learn the quantum infinite deep quantum neural net. So this is a result actually just published by Caltech's
Robert paper.
Robert Huang, sorry, not Robert Yang, Huang, and the entitled Power of Data in Quantum Machine Learning. So it has the theoretical the derivation of the result. The whole paper is basically about why the quantum kernel, the squared quantum kernel, is more powerful, and it's particularly proposition 3. So that was a pretty kind of deep result. I just want to mention that. Thanks.
Okay, thank you for this the comments for this part. Thank you so much. Okay, but Haq have more context to introduce. So maybe it's the time is given to Haq. Maybe you can start it. I'll just stop my share and you can start your work.
Okay.
Thank you.
If you have other questions, you can post in the chat room, and after my part, we can still have some time, like Jun answer, so I'll answer those questions. All right, so let's have the second pass, second part of this. Right. How to share it? Sure. Okay. It looks like I have some access issues. All right. Let me share the screen. Can you see my screen right now?
Okay, no problem.
Okay, cool. Okay, let me find a slide. All right. So hi everyone, welcome to the second part of this tutorial, quantum machine learning for speech and language processing. So for my part, there'll be application and some practice feeling when we do this kind of research related to quantum machine learning. So before I start my talk, I want to give an overview about quantum machine learning as a solution from 2018 to 2023. So if you look like this diagram, we can find that mostly consider a speech recognition task from CTC to RN transducer and the joint supervised and unsupervised ASR like JOST. So we can see there is performance boosting, right, like year by year. So right now we take advantage from this DNN-based architecture. But meanwhile, if we look at this figure, on the orthogonal of this axis, we also have some kind of characteristics driven task. For example, we want to reduce time capacity, sample capacity, improve data encryption, and somehow improve security issues. So I would say some of the work is trying to addressing these issues not come from one orthogonal like result, trying to combine some quantum property. For example, like our work in ICAS 2021, we use a quantum encoder, but that encoder is in a separate machine. And to do this data isolation and trying to improve some security condition. And in the CVPR 2022, there's another paper like simulate image patches as a token with a weight function that outperform the swing transformer. So I would say this kind of research got this inspiration from quantum, but the model is not fully quantum machine learning based model. But we can see by incorporating a little bit about this quantum property, like our model can get both have improvement on the performance driven task and also adding some ingredient on some special using condition. But meanwhile, I would say if you coming from a quantum computing community, the main challenge and the big challenge you want to resolve is still more fundamental. For example, we do know before 2000s, there's in 19s there's some original paper describe how to use quantum algorithm to classify phoneme. And more recently, in Google, they have a quantum supremacy paper. So for those models, they are purely quantum, and the problem they're gonna tackle is like is hard to reserve on the classic machine. So in this way, this push the horizon about the task we can reserve. So now when we look at this solution, we can actually when we mention quantum machine learning, which is take advantage of quantum computing. Right now, due to the hardware constraint, we could not directly do those problems like the red dots, like the purely quantum circuit or quantum kernel things. But meanwhile, the hardware like revolution is pretty fast. Like you can think about like a decade ago when people were working on DNN, so we can actually do some pioneer work trying to combine these things together. So for today's talk, I will give some recent example how and where people can conduct research. I mean, like if we consider as a researcher, we want to step in this new quantum machine learning community or trying to doing some quantum machine learning application, I would say right now it's not purely performance driven task. For example, if you really want to use a pure quantum model, the thing you can deal with is actually molecular data and some quantum format data, which is a popular track in New Ridge and ICML since this year. as a speed researcher, right now we are focused on production-driven task. So I would say here is something we should focus and look at during today's talk. So again, I want to mention some fundamental question. So why should we do quantum machine learning research? Let's say maybe next year. So I would say we're trying to reserve some question that cannot be done with classic CPU. For example, with quantum machine and quantum simulate QPU, we can actually dealing with the data with complex phase information, and we can process this quantum format data directly. And the second thing why we do this kind of research is we're trying to incorporate this quantum property into deep learning solution. That's for example, I say by using quantum machine, you projecting those features in a high-dimensional hyperparticle ball, so you can have a better representation power when you separate those features, and you can do the encryption and data isolation, which could not be done with the classic algorithm. And another question I would say a lot of researchers are interested, maybe mostly today, is how can we do quantum machine learning in 2023? I would say mostly there is some CPU-based QPU simulation. Right now, actually, there is a TensorFlow quantum package, which you can directly do some quantum circuit training and even train with means with your quantum-based model directly. And meanwhile, there's also a PyTorch-based solution called Pennyline. I would say you can first use a CPU-based QPU simulation for your work. And also, they have TPU-based simulation. For example, you have ASIC, which trying to accelerate this tensor computation progress when you do this quantum simulation. Finally, for the real application, there will be Qiski and BNQ. That's for the real quantum machine. So I hope if you get nothing from this tutorial, these 2 pages help you understand what kind of research we can do and what the thing we're going to talk in the following maybe 1 hour. All right, so as an example, I'm saying, okay, so there is some preliminary work, how this work look like. So I would say right now, in recent 2 years, quantum mainly be considered as a feature extraction for both acoustic and language information. For example, you project those acoustic feature and language embedding the latent space, and then by having this projection, people find out, okay, there is some slight improvement when you certainly mapping back this feature with your classic classification algorithm. I will talk about this detail, but it's one kind of main category. And also there's a quantum as hyperplane modeling for kernel learning. Right now, there's one paper for speed recognition just released today. Is one of my side project when I was interning Google. So we find out, okay, with quantum kernel learning, we can do this kind of separation for low resource language. And also, thank you, my advisor, Professor Lee, we do this kind of research. And the third part is another thing right now is adding some nonlinearity for hyper quantum classic modeling. I would say quantum is a tool when we mapping this data in the high dimension space and mapping back. But meanwhile, there's some recent discussion saying, okay, this mapping is actually losing don't have this kind of nonlinear transform. So there's some paper just discussion these issues, like a June's discussion and one paper in NeurIPS last year. So I would say these 3 kind of main category like way you can do this kind of research. So the first one is kind of low-hanging fruit, and the following 2 is much fundamental. I'm going to review that. All right. So in this 1 hour, so first I want to talk about the background about quantum computing and why did quantum computing motivate us to kind of revolutionize our new design for machine learning. And the second, we're going to talk about quantum machine learning to a perspective of representation learning. And finally, I will provide some little bit implementation saying how we can implement those hybrid quantum machine learning as a part of this tutorial. So I would say, since we still have time, so if you have question, you can leave your question in the chat room, and I will try to answer that even after this tutorial. Okay. So let's go to the first part. So the background would say what kind of data and algorithm we are looking today. So for when we talk about quantum machine learning, there are actually different diagram we can look at. For example, the data can be quantum like this, but the algorithm can be also quantum. And for the classic algorithm we're gonna dealing with is actually the data is a classic format. Classic format means like 0 and 1 and in the bit format, and algorithm is also in the bit format. And for the red one, you can think of some physical data have to use some specific like high dimension methods we're dealing with. But we also look at today is actually the data is quantum, and people use some classic algorithm like deep neural network to dealing with this black hole data. That's one example.